Understanding Slip on Triggered Faults in the Presence of a Large Regional Deformation by Moises Ponce Zepeda. On April 4, 2010, a magnitude 7.2 earthquake, since known as the El Mayor Cucapá earthquake, occurred in northern Baja, Mexico. It occurred on a north-south trending, right lateral oblique normal fault. Slip associated with the El Mayor Cucapá event is on the order of 3 meters, whereas slip on the faults north of the rupture is measured at about 5 centimeters. Here you can see what kind of displacement looks like in the field. This is a portion of the Borrego Fault that ruptured with an average height of 1.5 meters, or about 5 feet. This inset contains a small portion of the interferometry gathered shortly after the El Mayor Cucapá event. The event was the first earthquake deformation captured by UAV SAR data. Using data acquired north of the U.S.-Mexico border on both October 21, 2009 and April 13, 2010. By analyzing UAV SAR data, it is possible to note slight deformation in the crust, telling of interacting forces within an accuracy of 2 to 3 centimeters. If the two samples are separated in time and the terrain is shifted between observations, it will return a different phase. The amount of shift required to cause a significant phase difference is on the order of the wavelength used. This means that if the terrain shifts by centimeters, it can be seen in the resulting image. Each colored contour or fringe of the interferogram represents 11.9 centimeters or 4.7 inches of surface displacement. About 20 millimeters of uplift occurred in the Salton Trough surrounding the main shock, but began since as early as March 2011, as observed by GPS observations. This is a previously undiscovered Yuha fault, as noted in the USGS Open File report published in 2011. Each of the noted observation points were noted in the field shortly after the earthquake. This is the LiDAR data that was also captured shortly after the earthquake, demonstrating where the ruptures took place along the visible fault scarp following the earthquake to give you a context as to the length of the rupture and the amount of the displacement. Faults are seen as black or dark against a silver or gray background. Light detection and ranging topographic survey of the El Mayor Cucapá earthquake revealed a 120-kilometer long multi-fault rupture through the northernmost portion of Baja. This differential LiDAR survey captures an earthquake surface rupture in a sparsely vegetated region with pre-earthquake lower resolution LiDAR data. This is the northwest end of the rupture along the Borrego Fault, and fault scarps are seen progressing up the hillside. Modeling earthquakes. Using a program called Dislog, part of the QuakeSim suite, we are able to construct forward models of waves published data. I am using a 4-fault model in order to understand the resulting crustal deformation changes in the Salton Trough, which are reflective of changing stress. By taking the data and modeling it on a segment-by-segment basis, it is possible to eliminate the overprint stemming from the larger Laguna Salada fault and display how it interacts with other faults in the Salton Trough. This display models all faults regardless of depth at the surface. However, each fault segment displayed is a 3x3 kilometer segment in 3-dimensional space, complete with depth and dip as initially modeled. Analyzing the release and modeling its progress along the select fault segments in the area allows for a better understanding of both the event itself and the balance of stress in the area currently. Forward modeling. On the left is a dense model with many observation points. As a result, the interferograms have smooth color progressions that are easier to read, containing densely packed information. Dislog computes surface deformations for a point source or finite source using Okada's method for modeling surface deformation due to shear and tensile faults in an elastic half-space. Models can take multiple fault inputs and will sum the components to give the total displacement and strain. In the bottom right is an output plot from the portal that superimposes both the vectors of motion in addition to the interferogram of crustal motion. Upon closer inspection, the rupture points become apparent on the synthetic interferogram as evidenced by the sharp changes in color. A Accounting for overprint. The large signal superimposed over the much smaller signals makes it difficult to infer behavior on the responding faults to the north. Constructing models will both test the level at which we can invert for slip on the corresponding faults north of the rupture. From the dense synthetic interferograms, it becomes clear from crustal movement where separate faults occur. QuakeSim uses information gathered from UAVSAR as part of its algorithm in order to build the synthetic interferograms. INSAR stands for Interferometric Synthetic Aperture Radar. Satellites record images of the Earth's surface, and these images can be combined to show subtle movements on the ground surface called deformation. In the area highlighted, it becomes much more apparent that there is a break in the surface as reinforced by unexpected color bands from the satellite interferogram that is also represented in the models and synthetic interferograms. In the area highlighted, it becomes much more apparent that there is a break in the surface. Here is a fault map from the parameters published in the Open File Report, measured in the field, and here's how they match up with the interferometry gathered from the satellite. This is a model of the displacement that is left lateral taking place along the newly discovered Yuha fault, as visualized in an interferogram with less line-of-sight observations. This is a more dense observation of the motion taking place along with vectors drawn as arrows that explain the left lateral slip. Inverse modeling. Inversion starts by submitting a guess as to the parameters of a fault in the general area and expected values therein. The parameters necessary to construct a fault are an origin point and relative distance, strike angle, depth, width, length, strike and dip slip parameters. Next, we input observations. For our models, we use line-of-sight observations gathered from the synthetic interferometry observation point grid we defined in DISLOC. These observations rely on having an observation type, relative location, line-of-sight parameter gathered from the data, elevation, and azimuth. The project parameters consist of a name for the model, the maximum number of iterations used to try and find a good fit for the model, and an origin point. The fault components inputted earlier are then listed, with the option to have Simplex's algorithm vary for the inputted values in an attempt to make the model fit the observation provided. Finally, Simplex is ready to run, and provides an inversion model of the faults that would cause the crustal deformation observed. Simplex also sends an email letting you know when the run is complete, because sometimes it takes a while to compile all of the information. Here is the output showing the location of the fault that Simplex inverted for in comparison to the fault that was originally observed in the field. Our coefficient of determination, or R squared, is 0.174673. Our estimated offset is 0.0972904. Our best ever chi-square was 366.546. The more dense the observations become, the higher the chi-square value, and the lower the estimated offset. The northern end of the Yuha fault that we inverted for was 4.51 kilometers from the documented results, which could be a result of the line-of-sight data needing more observational points, or perhaps deeper slip or a migration of slip. However, further modeling would provide more insight.